Hello there everyone, thank you for joining me today as we review some derivative rules and mechanics. You can see the objectives for this review lesson listed down below. Let's warm up with a little bit of average rate of change here. So back at the beginning of chapter 2, we started that chapter by discussing the average rate of change, which we can calculate using our good old-fashioned slope formula. So to find the average rate of change of a function over an interval from a to b, we calculate the rise over the run over that interval, f of b minus f of a over b minus a. So for this particular problem, finding the average rate of change of e to the power of x cosine x from the interval from 0 to pi, here's our a, here's our b, here's the function in question. So let's calculate f of b, that's f of pi, minus f of a, f of pi, sorry. Okay, f of a, yikes, e to the power of 0, cosine 0, over b minus a, pi minus 0. A little bit of trig work here now. Cosine of pi is negative 1. E to the power of 0 would be 1. Cosine of 0 is also 1. All of this would be over pi then. We're looking at negative e to the power of pi minus 1 over pi for that average rate of change. F of b minus f of a over b minus a, where a and b are the endpoints of the interval. That's how we calculate average rate of change. We'll see this again a little bit later when we talk about the mean value theorem. So after we discussed the average rate of change in chapter 2, we discussed the instantaneous rate of change, i.e. the derivative. And of course, at this point, we know all of our derivative rules, all of our shortcuts. But back at that point in time, we first discussed the definition of the derivative, finding the slope of the tangent line as we pick 2 points closer and closer to each other using that idea of a limit. All right, now the definition of the derivative is shown in the top right corner. To get right to it here, when you see a question like this on the exam, we have to recognize that although this question might look a little bit intimidating, at the end of the day, this is asking us for the derivative of, okay, and look at the function that's being used here. It's natural log. It's natural log of x plus h minus natural log of x, right? Where x is 4. So this is asking for the derivative of natural log at x equals 4. That's all it's asking for. So if the function f of x is natural log, the derivative then, f prime of x, well, our rule for natural log is 1 over x. And so f prime of 4 then would be 1 over 4, which is one of our multiple choices. When you see this question, think definition of derivative. You just have to identify what the function is and then potentially a specific x value that you're supposed to plug in. We then discussed what it means for a derivative to exist at a given point. In other words, we discussed differentiability, right? And in the top right corner, you can see the graphical representations of situations where a derivative does not exist. If we have to show it on a question like this, we have to think about the derivative of the function as we approach a specific value from the left and from the right. Now, this question is also asking us about continuity, so a little bit of good review there, right? Let's check the continuity piece here first. In order to check if a function is continuous, we're also going to be checking this at the same time. We're going to see if the two-sided limit at x equals 3 exists using one-sided limits, and then we'll check that against f of 3. So let's check the one-sided limits first. Let's think about the limit as x approaches 3 from the left of this function. Well, we'd be using the top piece there where we plug 3 in for x, and 3 plus 2 is 5. Now check the limit as x approaches 3 from the right. Well, from the right, we'd be using the bottom piece and the piecewise there. 4 times 3 is 12. 12 minus 7 is also 5. Okay, this shows that statement number 1 is true. The two-sided limit at x equals 3 exists. To show statement number 2 is true, to see if it's true, we got to compare this against f of 3. Make sure there's not a removable discontinuity there. Well, when there's only 2 pieces in the piecewise and we have that equal to here, this is going to be trivial because f of 3 would be then 3 plus 2, which is 5. And so there's not a hole there. This function is continuous at x equals 3. To check statement number 3, we got to think derivatives now, of course. It's saying differentiable, right? So let's take the derivative of this piecewise function here. The top piece would have a derivative of 1. Derivative of x plus 2 is 1. The bottom piece would have a derivative of 4. This is for x values here and for x values here. Well, we could write it down more formally if we want to using one-sided derivatives, but if you look at this, the piece from the left has a slope of 1, the piece from the right of 3 has a slope of 4. Those are different slopes. The one-sided derivatives are not equal here, so statement 3 is not true. F is not differentiable at x equals 3, and so only statements 1 and 2 are true here. So after discussing differentiability, we then moved on to various derivative shortcuts. And these are not all given in order. Some were in chapter 2, some were in chapter 3. But here is basically a summary of some derivative rules that we should know in preparation for this AP exam. Okay, I'm not going to talk about every single one here, just reminding you of some of those rules. We're going to practice a couple of them, not all of them. It'll be too long of a lesson here. Let's practice the product rule first. So here we are asked to find the derivative of a product, and so we apply the product rule, which is shown in the top right corner there. It's the first function times the derivative of the second, plus the second function times the derivative of the first, right? So let's get after it here. We got our first function, cosine, times the derivative of the second. Got to know your derivative rule for tangent, secant squared. Plus the second function, which was tangent, times the derivative of the first, and the derivative of cosine is negative sine. Now, none of these match any of the multiple choices. This is a situation where knowing some trig identities can help us out. If what we have doesn't match any of the multiple choices, we need to simplify this trig expression, which is something we practiced in previous courses, but it's been a little bit. One tip to help with that can be to rewrite all of these in terms of sines and cosines. For instance, secant squared, it would be 1 over cosine squared, being that secant and cosine are reciprocals. Tangent is equal to sine over cosine. Now this power of cosine here will cancel one of those powers of cosine there. So just scooting down now, we've got 1 over cosine plus, this would then be, I guess, negative sine squared over cosine if you multiply these two together. We have a common denominator, so we could write this as a single fraction now. And this expression in the numerator might give you a pause because this is one of our Pythagorean identities. If you work with one of the Pythagorean identities, 1 minus sine squared x is equal to cosine squared x. And so we have cosine squared x over cosine x, which we reduce down to just 1 power of cosine x, which is choice B. The calculus gets you this far. After that, it's some trigonometry work with some identities that we need to know. Another specific rule for derivatives is our quotient rule, right? You can see it read in the top right corner there. The way I typically teach it is kind of crude, but I'm going to say it anyway, kind of simple. Low d high minus high d low over low squared. Simplifying things quite a bit there, but it works. So let's apply that to this function f of x. We want the instantaneous rate of change at x equals 2. We'll find the derivative and we'll plug in 2. So our low is our denominator, high is the numerator. So let's apply our quotient rule here. We're going to have low, x minus 1, d high, derivative of x squared minus 2 is 2x, minus high, d low, derivative of x minus 1 is 1, all over low squared. Now you could simplify this here if you want. Remember, at the end of the day though, we're trying to find the instantaneous rate of change at x equals 2. So maybe let's just plug in 2 and start working with some numbers as soon as we can. We got 2 minus 1, 2 times 2, 2 squared minus 2, all over 2 minus 1 squared. What do we have here? We have 4 minus 2 over 1. That's 2 over 1. That's 2. Quotient rule, low d high minus high d low over low squared. Remember, it's often possible to rewrite your quotient as a product using negative exponents, in which case you could use the product rule and maybe the chain rule, right? But here we applied the quotient rule. Speaking of chain rule, this is a very, very, very important derivative rule for us to know because we often work with compositions of functions and derivatives. And that's exactly what the chain rule does for us, helps us to differentiate compositions of functions. Okay, you can see the rule expressed pretty formally in the top right-hand corner. It's the derivative of the outside evaluated at the inside times the derivative of that inside, right? Now here, this function f of x is a composition of actually 3 different functions. I see 3 pieces to this. f of x equals, we've got e to the power of, we've got tangent, and tangent is being squared. So in terms of working my way from the outside in, I think I'll go in this order here. So here goes. F prime of x is equal to derivative of the outside, that's e to a power. Well, our derivative rule for e to a power is to keep e to that power, but then multiply by the derivative of that power. And that's where the next part of the chain rule is coming in. Now, the derivative of that power is itself a composition, so we got to differentiate tangent of x that's being squared. Well, we differentiate that squaring function by bringing the 2 down in front, subtracting 1 to get the new exponent. But then we've got to multiply by the derivative of the very inside there. That's the expression I underlined 3 times, and the derivative of tangent is secant squared. If I try to kind of underline again, this is where these pieces are coming from. Now, does that match one of our multiple choices? Yes, it does. Choice D. Chain rule is very important for us to know. Another type of differentiation important for us to know is this implicit differentiation. We use this when our function is not given explicitly as a function of just x or just y, rather when we have the two variables mixed together like we do here. So we've got this curve given implicitly. We are going to use implicit differentiation to show that dy dx equals the expression given. So let's get to it here, working from left to right. Our derivative of x squared, we just say 2x for that. Now, the derivative of 4y squared, we apply the power rule to get 8y, but then this is where we can fall into a trap if we're not careful. We don't know exactly what y is equal to in terms of x, and so we apply the chain rule there, technically, and we just say that we'd multiply by the derivative of the inside, the derivative of y, dy dx. On the right-hand side, the derivative of 7 is 0. That'll go away. 3xy is a product, and I'm going to think of it as these two factors. So my product rule says first times derivative of second plus second times derivative of first. Excuse me. Now we've done our differentiation, but we have to show that dy dx equals this exact expression. So a little bit of algebra work now. We get all the dy dx's to one side. So 8y dy dx. Let's bring this 3x dy dx over. Everything with dy dx to one side, everything without a dy dx to the other side. The thought is then we can factor out that dy dx on the left and then divide by the terms that would have been left in parentheses. I'm doing 2 steps in one to save a little bit of time. And when you divide by those terms, you get the exact expression we were supposed to get. I did not show the factoring step there. I skipped it to save a little bit of time. This is kind of a unique concept, but it may show up and I want us to be prepared for it. So a function and its inverse are obviously very much related to each other in a number of special ways, and it's not the same thing can be said for their slopes, for their derivatives. So here's a question where we're given some information about f. We know that g is the inverse of f. We want the value of g prime of 3. We don't know the actual function rules here, but we have enough information provided we understand the relationship between the slopes of these two inverses. Here's how I like to write it down. We're trying to find g prime of 3. In other words, we want the slope of g at the point where x is equal to 3, some y coordinate there. Well, the relationship here is that that would be the reciprocal of the slope of its inverse f at the point where y is equal to 3. You know, a function that's inverse symmetric across the line y equals x, x's and y switch roles. That's the relationship there. Okay, now to find the slope of f at blank comma 3, we have to know what this blank is right here. Well, let's go back to this for a moment. Okay, the slope of f at blank comma 3, we're looking for where f has a y coordinate of 3. Well, here's a y coordinate of 15. Here's a y coordinate of 3 where the x coordinate is 6. So we're trying to find the slope of g at 3 comma 6. That's the reciprocal of the slope of f at 6 comma 3. Well, we know the slope of f where x is equal to 6. We're told that. That slope is negative 2. And so we get our multiple choice here. Kind of a unique situation, but it's cool to know, and it may show up, and I want us to be prepared for it. Just a couple more concepts here, a lot of information. Thanks for sticking with it. Okay, after we learned how to take derivatives and find instantaneous rate of change, we spent a good deal of time practicing writing tangent line equations. We're going to practice that here. Now, to write the equation of a tangent line, same as writing the equation of any line, it can be helpful to have a point to work with, the point of tangency, I would say, and then we need to know the slope of our tangent line. And once we get that information, we may be able to eliminate some multiple choices, but we're going to pretend for a minute that this is not a multiple choice question. Now let's start with our point. We know that x is equal to 1, but we should have the y coordinate as well. So we're going to take 1 and we're going to plug it into this function up here, do a little bit of arithmetic, and when you plug 1 in, you'll get an x value, a y value of 2. So our point of tangency here is the point 1, 2. Okay, I'm going to underline that twice. We're going to use that. The slope of our tangent line requires us to find the derivative of f. We want the slope of f at the point where x equals 1. We need the derivative of f. Now, f is this product here. In a pinch, if I forgot my derivative rules, I guess I could expand this and then FOIL, and oh my goodness, that would take a while though. Instead, I'm going to treat this as a product and use the product rule. There'll be some chain rule mixed in here as well. So product rule says take the first function, 2x minus 1 to the 5th, times the derivative of the second, and the derivative of x plus 1 is 1, plus the second function, which was x plus 1, times the derivative of the first. Now, the derivative of the first, that 2x minus 1 to the 5th, I'll need the chain rule there, so the 5 will come down. We'll have 2x minus 1 to the 4th then, but the chain rule says multiply by the derivative of the inside there, and the derivative of 2x minus 1 is 2x. I could try to simplify this algebraically here, but at the end of the day, I want the slope where x is equal to 1. So let's start work with numbers as soon as we can. Let's plug 1 into this. Okay, and to save a little bit of time, because you can do the arithmetic, if you stick 1 in for x and you calculate all of this, you'll get a slope of 21. So we need to write a linear equation with a slope of 21 going through the point 1, 2. Well, if the slope is 21, we can eliminate these three. Okay, don't fall into this trap. The y-intercept is not 2. Y is equal to 2 when x is equal to 1. Even from there, I might wager a guess at point B. But just to show that, let's do a little bit of point slope work here. Y minus the y coordinate equals slope times x minus x coordinate. Do a little bit of algebraic manipulation here, and yep, you will get that choice B. Near the end of actually it was later in chapter 5, now that I think about it, we talked about this mean value theorem, which is kind of an application of derivatives in a way. The mean value theorem is shown graphically here and kind of algebraically inside the box there. The mean value theorem says if a function is continuous on a closed interval and differentiable on the interior of that interval, then at some point in that interval, there's some point where the instantaneous slope at that point is equal to the average slope over the entire interval, shown by the secant line and the tangent line to the right, shown by this equation right here. So we've got this multiple choice question, f of x equals x cubed. The application of the mean value theorem on the interval 1 to 3 guarantees a point in that interval at which the slope of the tangent line is equal to which of the following? Well, this problem doesn't have much to do with a graph per se. We're not given a graph. I'm not going to sketch a graph when I don't need to. I think we can use this algebraic interpretation right here. The conclusion of the mean value theorem here would tell us that at some point in the interval from 1 to 3, there's going to be some x value, call it c maybe, that's equal to the average rate of change on the interval from 1 to 3. And we practiced finding average rate of change earlier in this video. Here's the average rate of change on the interval from 1 to 3, where f of x is x cubed. And 3 cubed is 27, 1 cubed is 1. We get 26 over 2 here. So at some point on the interval from 1 to 3, there's some x coordinate where the slope at that x coordinate is equal to positive 13. The mean value theorem, one of the major theorems in this course, a theorem that we need to know. Okay, one last problem here. After we talked about derivatives, we then connected a function to a function's graph to the derivative and even the graph of the derivative itself. Here's a situation where we have the graph of the derivative of f, and we are asked some questions about f itself. It's important for us to recognize the graph in front of us is not f, but rather it's the slope of f, it's the derivative of f, and we need to analyze that to answer the questions below. A question like this is maybe good to go through just one step at a time here. So statement 1, f is continuous on the open interval from a to b. We got to remember that connection between differentiability and continuity. If a function is differentiable on an interval, then it's going to be continuous on that interval. And I would claim that f is differentiable from a to b because f prime exists from a to b. The graph of f prime has no holes, no jumps, no vertical asymptotes. Okay, so this is a true statement. Yes. F is continuous because f is differentiable. I can tell f is differentiable because f prime is one smooth continuous curve there. Statement 2, f is decreasing on the open interval from a to b. F would be decreasing where f prime is negative, and f prime is negative over here, but f prime is positive over here. So statement number 2 is not true. F is decreasing for a little bit, but not the entire interval. Finally, statement 3, the graph of f is concave down on the open interval from a to b. Concave down would be indicating that f prime is decreasing. That's one definition for being concave down. Well, is f prime decreasing? Yeah, f prime is decreasing on this entire interval. So this is a true statement. Statements 1 and 3 are true here. Statement 2 was not. That was a lot of information about derivatives in what I wanted to be a short amount of time, but ultimately wasn't. Thanks for sticking with it here as we reviewed derivative rules and mechanics.